what is the schematic structure of a quantum computer? Again, we have an input, but this time the input may consist of both classical information, so that's still possible that we input classical information, or quantum information. And quantum information means quantum states. Typically, both classical information and quantum information is encoded in states of qubits. The qubits are the two-level systems that we discussed extensively last week. There's an example that I added here. This is an example for classical information that you input in a quantum computer. You can represent, for example, the number 21 as a binary form. That's 10101. That's the binary representation of 21. And you can encode that in a quantum computer in the basis state 10101 of 5 qubits. Yeah. So in general, classical information that you input in a quantum computer is just encoded in basis states of multiple qubits. But you can also input superposition states, and this is then true quantum information, and then the input is a qubit or multiple qubits in some superposition state. Now, this goes into the machine, and a quantum computing machine performs a unitary transformation on the qubits. So you have, in this example, you have 5 qubits. So the system lives in a 5-qubit Hilbert space. Yeah, that's a Hilbert space of dimension 2 to the power 5. It's a pretty big Hilbert space. And in this Hilbert space, your quantum computer does a unitary transformation. Already at this point, we come back to the issue of reversibility versus irreversibility. A unitary transformation is always reversible. There always exists an inverse. And therefore, this core of a quantum computer always works in a reversible fashion, in contrast to a classical computer, which has a lot of irreversible gates. After this big unitary transformation, we have an output, which consists in the final state of these qubits. And at the end of the day, however, we typically want to extract classical information. Say we want to factor the number 21 in its prime factors, so 3 times 7. That's the kind of output that we would like to have. So a final state of qubit is not yet a classical answer to our classical question, our classical problem. So there has to be a further step in which we extract from the final state of the qubits classical information, and we do that via measurement. Typically, this measurement is done in the standard basis of the qubits. Now, the measurement, that's the component of the quantum computer that introduces an element of irreversibility. Because when you do a quantum measurement, then from the output of the measurement, in general, you cannot infer the quantum state that you had before. Yeah. So if you have a superposition state of spin up and spin down, you measure the spin of the system, you find spin up, let's say. Then from this result, you cannot reconstruct the respective amplitudes of up and down that you had beforehand. So this is an element of irreversibility. And furthermore, this introduces a probabilistic aspect, because whenever you have a superposition state, then you obtain a given measurement outcome only with some probability and not with certainty. That's the reason why the typical quantum computer and the typical quantum algorithm works in a probabilistic fashion. Yeah, so with a few exceptions, the quantum computation is probabilistic, in contrast to sort of the vast majority of classical computation. This further implies that in a single run of a quantum computer, you rarely get immediately the answer that you're looking for. But you have to run it repeatedly. You have to collect a sufficient number of data, measurement data from repeated runs, in order to be able to identify the most likely solution of your problem. Yeah. Still, I mean, we will later on, we will talk about specific examples of such algorithms. Of course, the whole hype about quantum computing comes from the fact that you can solve some problems more efficiently and more quickly, at least on paper, than a classical computer. And this is despite the fact that in many cases you have to run the algorithm many times. Now, a very fundamental result that I will not prove during the lecture, but if you are interested, you can find the proof both in my manuscript that I uploaded to OLAT, and you can also find it in, for example, Nielsen and Chuang, the major reference in the field. There's a fundamental result that says that in complete analogy with the classical case, where arbitrary Boolean functions could be built up from just a small set of logical operations, each involving just 1 or 2 bits at a time, you can prove in the quantum case that an arbitrary unitary transformation in an n-qubit Hilbert space can always be built up from elementary quantum logic gates, which also involve only 1 or 2 qubits at a time. As long as we talk about building up any unitary transformation from just gates involving 1 or 2 qubits, this is an exact result. However, it goes one step further. I will come back to that a bit later on, that regarding, we will see that there are infinitely many single qubit and 2 qubit gates, because you have infinitely many possible unitary transformations. You can reduce that further, and you can say you actually need just a handful or very few single types of single qubit gates and 2 qubit gates. And this second part of the result, that holds within an arbitrary small error. So you can make it as small as you like, as long as it is not exactly equal to 0. Okay, so this is the quantum circuit model. Each gate in itself is reversible, and the whole unitary transformation is reversible. And I have mentioned this already a couple of times because it's just a very important aspect. One thing that is not easily possible, in contrast to the classical case, is you cannot simply copy qubits the way you can copy classical bits. So this is important to keep in mind.